So hopefully short presentation, going through some slides that have been uploaded to our pubs, and this will review some of the big ideas in database design illustrated with the so-called STATS19 dataset. The STATS19 dataset is called STATS19 because that's the form that the police used to fill in when a road collision was reported to them, and it eventually ends up in a database that bears the name of the form that once upon a time was filled in. So in that context, first piece of jargon to look at is the idea of entities, attributes, and relationships. So the entities are real things that form rows of tables in a database. The tables are tables of real things. So one example is a collision. A collision is an event in which a person is injured. As it says there, STATS19 is using the outdated terminology accident. So we talk about a table of accidents, and there is a unique key for that table, which is the accident index number. And each row in that database, as I said, is one event. And there is separately an entity of a casualty, and these are people who have been injured in a collision that has been reported to the police in the UK. And a unique key for that would be both the accident index number and the casualty reference number. So the casualty reference number is the number of the person who was injured in a given accident. So each row in the casualty table is a different person. And then we have a vehicle table, which gives information on all the vehicles. So the unique element is a vehicle involved in an accident. A unique key will be accident index number and vehicle reference number. And this contains information on both the vehicle and the driver of that vehicle. So the entities, these are the real things that we form into tables within a database. Attributes are properties of these entities. So we have information on casualties. Each row represents a casualty. We will have things such as their age, their sex, what class of casualty they were, whether that was a pedestrian, passenger, or a driver, rider. And likewise for vehicles, we have attributes such as what type of vehicle it was, and again, the age and sex of the driver. And then, as well as having these entities, so an accident or a collision, casualties that are involved in those collisions, and vehicles that are involved in those collisions, there are also clearly relationships between them. And every accident, every row in the accident table can have one or more casualties associated. If there's no casualties, road collisions don't get reported to the police. So by definition, there has to be one or more casualties. And we can denote this one-to-many relationship using the notation within the brackets, 1 asterisk. It tells us one accident, one or more casualties, any number of casualties. And likewise with the vehicles, there will be, for every accident, there will be one or more vehicles that are involved. And how do we understand the relationship between casualties and vehicles and the accidents? They're identified by the accident index number. So the primary key for the accident table serves as a foreign key in the casualty and the vehicle table, telling us which reported collision, which accident that casualty or vehicle came from. And also, there's further associations, because each vehicle and every row in the table vehicle, each vehicle that has been involved in a collision can have 0 or more casualties. And the notation for that is within the brackets 0, star, telling us that it's possible that a vehicle has no casualties associated with it, or many. And the vehicle table itself contains a foreign key to identify the casualty that's associated with that vehicle. That's the casualty reference number. And in turn, each casualty has exactly one vehicle associated with it, and a one-to-one relationship we denote with the 1,1. And again, the casualty table also has as a foreign key the vehicle reference number, so we can tell which vehicle is associated with which casualty. The one possibly minor complication about this is that within the STATS19 data, pedestrians who clearly weren't in any vehicle, they're associated with the vehicle that injured them. But we have relationships that can be one-to-one, one-to-many, and we also have the possibility with vehicles of a specific vehicle not having any casualties associated with them. So description of the various relationships that occur within this database, and we can depict this in what's called an entity relationship diagram. So by convention, the squares or the rectangles denote the entities. So I have entities which are accidents, and every row within that is a separate collision. I have an entity that is vehicles. Every row in that is a separate vehicle, and I have an entity casualties, and every row within that table is a separate casualty who's been injured. And the diamond shapes tell us something about how I understand the relationship between the two. So the accident reference number tells us the relationship between the specific vehicle and the accident in which it was involved. And we've got the notation telling us that's a one-to-many relationship. There has to be at least one vehicle associated, but there could be many. And finally, the relationship between vehicles and casualties, as we said, looking from vehicles to casualties, there can be 0 or more casualties associated with any vehicle. But looking in the other direction, there is always exactly one vehicle associated with every casualty. Now, the issue with attributes goes back to once upon a time, people were super efficient about how they designed their databases for reasons of disk efficiency. And we would have what we could call lookup tables. So in the STATS19 data, as it's supplied by the government at the moment, the column for casualty severity contains the values 1, 2, and 3. And they're used to tell us whether a casualty was fatally injured, seriously injured, or slightly injured. And what we could do if we were being very efficient with our database design is use a small integer type to store the 1, the 2, and the 3, and then have a lookup table which we could then join to tell us what the 1, 2, or 3 meant in terms of fatal, serious, or slight. And there's a little note there, if we were using SQLite, that's pretty much what we would have to do. We would have to have this lookup query, lookup table. The interesting thing is we don't have to handle attributes like that nowadays. So one possibility is we could just store fatal, serious, and slight as a string. Really, in modern database terms, the entire STATS19 database is quite small, and there would likely not be an appreciable performance penalty if we inflated the database size by storing fatal, serious, and slight instead of a small integer. And there's a little note there that there's some subtleties around the best way of doing that in text. Which string type is most appropriate here. But specifically in Postgres, we also have the option of using an enumerated type, the enum, and that will allow us internally to store 1, 2, and 3 as the storage type. But when we go to print out the results of a query or extract the results of a query, we're given the fatal, serious, and slight. In essence, it's handling a separate table and a lookup for us. There are reasons why you might want to use enumerated types. There are reasons why you might not want to use enumerated types. It works well for very many fields within the STATS19 data. One of the biggest downsides to using an enumerated type is that they're just very hard to change. But given the STATs19 data to us as non-Department for Transport analysts. It's updated very infrequently. It's not a problem to any possible downside of a change is only going to catch us out once every few years. So it's something we can absolutely manage to get the best of both worlds. Simpler, what looks like from a query point of view, a simpler database structure, even if internally it's the same, and we get the efficiency of file space. But if we were going to think about all these attributes in lookup tables, a few of the possibilities have been illustrated here, and again in an entity relationship diagram we'd use circles. So some of the lookup tables would have to use local authority and police force. The location of an individual accident, you're told which local authority at the district council level, which police force it happened in. You're given information on the road type. Was it motorway, A road, B road, or some other road? And it certainly for the first two there, you might have to use a lookup table rather than enumerated type. Looking at the vehicles and the casualties, we have the sex of the driver and the casualty. We can use ones and twos, or we can use an enumerated type there. Vehicle type is starting to get longer and might be something you have to use with a lookup table. Casualty severity is the one we've discussed, casualty class. Again, that could be done with an enumerated type. But if we were going to use all of these with lookup tables, which we would have to do in SQLite, you can see how quickly that entity relationship diagram is going to get a little complicated looking. So just to summarize that, this is a relatively simple database. There are only 3 tables. Even then, the entity relationship diagram is going to become unwieldy if we were going to draw out all the attribute tables that are possible. That complexity does exist, whether we use enumerated types to hide it or not, because the various attributes do change over time. One reason for maybe avoiding some of the complications of the attribute tables in terms of understanding a database is we might want to focus on relationships with data that go beyond the STATs19 data themselves. So within the STATs19 data, we are given geospatial and demographic attributes. We're given geospatial data on the location of the collision. We're given demographic attributes on the drivers and the casualties, and we're also given sometimes at the lower census super output area level information on the home address of aggregated to preserve anonymity, but the home address roughly of the casualties, which obviously when we've got that, we're very interested in linking that to other data sets. So one reason for preferring to keep the entity relationship diagram simplified is to focus on these other possible links outside those 3 tables. And it remains the case that using the enumerated types in Postgres saves a lot of work in writing queries. We don't keep having to join all these attribute lookups because the enum enumerated types take care of that for us. So the real power of SQL comes from being able to join these tables. There are plenty of demonstrator projects all over the internet where people are mapping the accident tables or they're doing counts on the casualty tables. But the real power comes from doing the joins. And I'm going to use this example to review the 4 types of joins that are available. Inner join, there's 1 inner join and 3 outer joins. And in SQL, you normally don't need to specify inner or outer. That's why they put in brackets. It's up to you if you find it clearer to write it out in full. But we have an inner join and left joins, right joins, and full joins. And the piece of jargon we need to be clear about here, left and right, this is purely a reference to which table we specify first and which we specify second. And that will become clearer when we have a look at some examples. Let's walk through some examples of all these kinds of joins. So for the purposes of the illustration, we're going to use the STATs19, but just going to make one little change, and we're going to break the link for pedestrian casualties between them and the vehicle. We're going to say the pedestrian wasn't in or on a vehicle, so we're going to break that link. We're only going to consider casualties that were in or on a vehicle. We're only going to consider a vehicle existing if the casualty class was driver or the casualty class was passenger. And what we're going to do throughout is we're going to take the casualty as our left table and the vehicle as our right table. As it says, no right or wrong way of making that choice. That's just what we're going to use for illustration. And further, for illustration, let's just think we've got a single accident, a single collision that's being described here, just to keep life simpler. So here is some fictional table. We have a casualty table, and the primary key for the casualty table is the CID, the casualty ID. So for this collision, we had two casualties involved, one a pedestrian and one a passenger. And for the vehicle table, there were 4 vehicles involved: a car, a bicycle, a bus, and another car. And you can see that the primary key there is the vehicle ID, sequentially numbered 1, 2, 3, and 4. And if we think about what's going on here, if I look at the casualty table, I have the Venn diagram shows me 2 casualties, one with a VID of 0 and one with a VID of 4. And the vehicle table consists of the 4 vehicles: vehicle 1, vehicle 2, vehicle 3, and vehicle 4. And the one that's in both the casualty table and the vehicle table is the overlapping case, the passenger who was in car number 4. And that's illustrated in the Venn diagram. And I'll come back at the end to talk more about the Venn diagrams as a way of, some people find this as a way of thinking about, useful way of thinking about SQL joins. But we'll look first of all at the inner join and look at the result. So the inner join, we're looking for entities that match in both tables. And there is only one entity that matches. We saw that in the intersection area of the Venn diagram. The passenger within vehicle number 4 is intersecting with vehicle number 4. So when I perform an inner join and join those 2 tables, I have vehicle ID 4, and I have some data that comes from the casualty table. There was a passenger injured, and I have some data that comes from the vehicle table. It was a car. The vehicle that they were in was a car. So that's the inner join. In terms of pseudocode for how we might run this query, it would be to select the variables, the columns I'm interested in from the casualty table, and I would join that to the vehicle table, and the join, what regulates the join, the relationship that regulates the join is that the vehicle ID has to match. And there's just a little footnote there to say in practice, I'd almost never be doing this for no accident. I would have to join on both the vehicle identifier and the accident index number. That's the pseudocode. And the interpretation of what I'm doing here is the inner join tabulates all casualties who are in or on a vehicle. So the inner join's giving us that intersection of the 2 tables. Now the left join, in this case, what I'm doing is I'm saying take every entry in the casualty table, and if there's a corresponding, whether there's a corresponding entry or not in the vehicle table, add that information to a further column. So as with the inner join, I get the information about the passenger who was in the car, but because this is a left join, I get every entry in the casualty table. So I have one entry that was vehicle ID 0, the pedestrian, and it tells me there was no matching information in the vehicle table. So the left join give me all the information in the casualty table. If possible, supplement it with data from the vehicle table if there's a match. And for pseudocode representation, select the columns I'm interested in from the casualty table. The from is my left table, and then left join the vehicle, and the relationship that I'm going to use is that the vehicle ID matches. And again, there's a caveat. If I was doing this for real, I would have to have an and term in my join. I would also want the accident. I would also want to join by accident index numbers. So the interpretation is the left join is tabulating all casualties and identifying which, if any, vehicle they were in or on. So if there is supplemental information in the vehicle table, that's added to the result set. And if there isn't any supplemental information, I get nulls for that part of the result set. A right join does the opposite. It takes all the information from the vehicle table, and if there is supplemental information from the casualty table, it adds it. So in this case, the car, there were no casualties. Car number 1, there were no casualties. Bicycle number 2, there were no casualties. Bus number 3, there were no casualties. It's only car number 4 that it tells me one of the casualties was a passenger. So that's the purpose of a right join. Take the vehicle table and add supplemental columns where there's a match and null where there's no match. And in terms of the pseudocode for writing it, again, select the columns I'm interested in from the casualty table. And this time I'm telling it to right join the vehicle table and then specify the relationship on which I'm going to make the matches. The interpretation, the right join is tabulating all vehicles and identifying which, if any, casualty was injured in or on them. And then finally, I have a full join, and this returns an entry for every casualty and every vehicle, and it matches them where possible. So it tells me, this result set tells me there was a pedestrian injured and they were not in or on a vehicle. It tells me that there was a car, a bicycle, and a bus involved. None of them had a casualty. And it tells me there was a car that contained a passenger. VID number 4 is the car that contains the passenger. So the full join gives me a row for every unique entity in either of the two tables, and it matches them where the entities match. And in pseudocode, as before, I select the columns I'm interested in from the casualty table. And now I have to say it's a full join to the vehicle table, and I specify the relationship that I'm going to join the two tables together with. And in terms of an interpretation, it says there, the full join tabulates all vehicles and casualties, and it identifies which vehicle had which casualty and which casualty was injured by which vehicle. So we can consider all of these as operations with Venn diagrams. And as it says there, if you don't find, there's a link to a blog post. If you don't find the Venn diagrams a helpful way of understanding SQL queries, it may be you're not alone. There's an interesting blog post to read. But if you do like Venn diagrams and you like diagnostics, there's a full illustration of the 4 what I would describe as analytical joins, as well as some tweaks that are useful for diagnostic purposes, and that's if you need it, there's a full summary of all possible SQL joins. We looked at essentially left join, the right join, the full join, the inner join, and the outer join. But the 3 that we didn't look at may be useful if you're trying to perform some diagnostics on a misbehaving data set. To summarize, the power of SQL comes through the way you can combine information from different tables. And the real power, what makes this more than a data storage and filtering and aggregating tool, the power comes through the ease with which you can join different tables together to combine information. And just because we've looked at joining one table to another, it's worth pointing out you can chain join clauses. So you can left join another table, left join yet another table. You can build these up as much as you want. If you want to make professional looking entity relationship diagrams, there are tools that help you do that. I would suggest sometimes it's more important to conceptually understand those parts of a database that matter to you. And I would suggest it's a really good time investment to be comfortable with constructing these joins. That the power of SQL comes from being able to just understand and understand as a concept what we're trying to do by the join, and then implement it in code. So there's some really good practice for doing some joins at PG exercises there. But being able to construct joins correctly rather than incorrectly makes all the difference between a powerful analysis and a junk analysis. And it's not just a case of knowing the SQL, but understanding what you want the SQL to do. And I think it's a really good investment of time to get this really clear by doing some practice and really mastering these joins and the relationships.